Hello and welcome to another session in physics. In this session, we'll be looking at the topic radioactivity, part 1. But before that, let us review the previous lesson. Welcome back. At this point, let us look at the definition of radioactivity. Remember, in our previous lessons, we've been talking about the energy levels of atoms and how isotopes, mass numbers, and atomic numbers help to give definite names to an atom. For example, in an element where we have hydrogen, the mass number is 1 and the atomic number is 1. But if this were to change to 3 and this one changes to 2, then this wouldn't be hydrogen anymore. It would have to result to a new element very close to this, possibly helium. And that is exactly what happens in radioactivity. Radioactivity, simply put, is the spontaneous decay, spontaneous depreciation, or the spontaneous disintegration of the nucleus of the atom of an element, during which it is able to emit what we call alpha, beta, or gamma rays, or a combination of any or all the three, with a release of heat or energy in the form of heat, that is thermal energy. Does this bring to your mind how atomic bombs and weapons of mass destruction are being constructed? Remember, in previous lessons we talked about fission and fusion, where we said fusion is a situation where one heavy nuclei is made to fuse or come in contact with another heavy nuclei, and both of them will have to release a huge amount of energy. On the other hand, fission was the splitting of one heavy nuclei into two or more simpler nuclei, with all of them multiplying themselves spontaneously. And this is the principle that atomic weapons and atomic bombs work with. You see, a simple atomic weapon, once it is detonated, it can result in the release of heat energy that will result in wanton destruction of lives and properties. Remember, we said radioactivity is the spontaneous decay or the spontaneous disintegration of the nucleus of an atom of an element with the emission of alpha, beta, or gamma rays, or a combination of any or all the three of them, and the release of heat energy. Now, these alpha, beta, and gamma rays are what we call electromagnetic radiations. And when they are subjected to a strong magnetic field, they deflect in different directions. As you can see from the diagram here, you'd notice that in the presence of a magnetic field, a radioactive atom can release energy, radiation, or emission of some new particles. Now, what you see here on your screen is called a radiation table, where we look at the nature of the radiation in question, the velocity, the effects of a magnetic field on it, the ionizing magnetic field, and the penetrating power of that radiation. So we have three main electromagnetic particles here in question: the alpha particles, the beta particles, and the gamma particles. So take time at the end of this lesson to go through them and look at their respective wavelengths, their velocity, their effects, and their penetrating power. I'd like to point out at this part that questions to be concentrated more on the strength of their penetration. Like, alpha particles have the smallest penetrating power, but gamma rays have the highest penetrating power as a result of their shorter wavelength. An example of gamma rays is lead, and examples of alpha particles are thin sheets. So get yourself acquainted with this. Alright, let's talk about what we mean by radioactive decay, the half-life of a radioactive material, and its decay constant. Now, I'd like to get this point across that radioactivity is a spontaneous process. And when we say it is a spontaneous process, we mean it is independent of external control. In other words, it is not affected by physical factors such as temperature, pressure, or by any chemical treatment. It is purely a random process, as nobody can predict which atom will disintegrate at any given point in time. Also, the half-life of a radioactive element, as the name implies, simply put, is the time that is taken for half of the atoms that were initially present in the element to decay. This rate of decay of radioactive elements is found to be proportional to the number of atoms of the material present. So put simply, if there are n number of atoms of a radioactive element present at a given time, t, then its likely number of disintegration per unit time or per activity is given by n directly proportional to the minus dn over dt. Now, the minus sign arises from the fact that the number of atoms is decreasing with time, and lambda here is a constant of proportionality called the decay constant. So dn here is more like using the differentiation method, where we have to do that with respect to the number of atoms present, and then the t, the time taken for half of these atoms to decay. So hence the decay constant is defined as the instantaneous rate of decay per unit atom of a substance. Decay constant is given by number of atoms disintegrating per second over number of atoms in the source at that point in time. Now, enough of the jargons, and let's take an example to put into perspective what we're actually trying to talk about. The question says that a certain radioactive element has a half-life of 10 years. And the A part of the question says, how long will it take this radioactive element to lose 7/8 of its atoms that were originally present in it? And the second part of the question is, how long will it take until only 1/4 of the atoms originally present remain unchanged? Let's take that one after the other. So what it simply means is that if 7/8 of its atoms has been lost, if 7/8 of its atoms has been lost, then what it simply means is that to make it 8/8 or equal to 1, it means 1/8 is remaining. 1/8 is remaining. That's what it means, because when you add 7/8 plus 1/8, since the denominators are the same, you're just going to have 7 plus 1, 8/8. Then 8 divided 8 is 1, which gives us that 1 atom. Remember that the half-life is equal to 10 years. So, but what it means now is that n/4 remains after 20 years. n/4 atoms will remain after 20 years. And then after 30 years, n/8 remains. As it keeps decreasing every 10 years, half of it depreciates. n/8 remain after 30 years. So what it simply means is that it takes 30 years for this atom to lose 7/8 of its atoms, and n/2 remains unchanged. After 10 years. n/4 remains unchanged after 20 years. So the answer is equal to 20 years. So this is the answer for the B part of the question. So the A part of the question, this is the answer to A part of the question, and this is the answer to the B part of the question. So it takes 30 years for the atom to lose 7/8 of its atoms, and then it takes 20 years until 1/4 of the atoms originally present remain unchanged. It takes 20 years for 1/4 of the atoms originally present to remain unchanged. Now let's talk about transformation of elements. Now, talking about transformation of elements, this brings us to the fact that there are two main types of radioactivity. namely natural radioactivity and artificial radioactivity. Natural radioactivity simply refers to the spontaneous disintegration of the nucleus of an atom, which is entirely a random process free from external interferences such as temperature and pressure, and in which alpha particles, beta particles or gamma rays and heat energy are released. When a radioactive element undergoes radioactive decay, it may either emit alpha, beta or gamma rays, and this changes the atomic number of the elements formed. Hence, a new element is formed. Remember, what gives nomenclature to an element is as a result of the atomic number and the mass number of that element. If this is altered, a new element is formed. So we say it has been modified beyond recognition. On the other hand, in artificial radioactivity, an ordinary material is made radioactive by artificial processes such as bombarding it with radioactive particles. Thank you for joining us in this lesson. To refresh your memory on what we've just discussed, please take the test that will appear on your screen.